Let's now take a look at this problem involving a confidence interval. We have a traffic study looking at safety device reaction times. This is a before and after scenario. And so let's kind of go through our checklist of things to think about before even starting the problem. This one is a confidence interval problem as opposed to a hypothesis test. So let me start writing that down. So this one's a confidence interval problem. This problem involves an average as opposed to a proportion. We're looking at the average reaction time of the device versus not the device. This is a two-sample problem because we're looking at, obviously, we're looking at reaction times with the device versus without the device. This one is two-sided or two-tailed. The way we can tell that is because this is a confidence interval. The confidence interval, so we have a confidence interval that's going to be centered on something so that we're going to be looking with the two tails. This one involves a small sample because the size of the number of participants is 15, that's less than 40. And because it is a small sample, this one will be a t-test. And finally, one last observation is that this is paired. This is a before and after scenario, so it's paired. Okay, so the data is in the screen here. Unfortunately, the decimal points got cut off, so let me make this a little bit wider. So 36.7, 36.1, 37.5, 35.8, and so on. Hopefully I typed all this in correctly. And so the first step is to get the differences. So I did that already on screen. 36.7 minus 36.1 is 0.6. 37.5 minus 35.8 is 1.7, and so on, filling across. So those are the differences. To get the confidence interval, the center of the confidence interval will be the average of the differences. So once I have subtracted, this now basically devolves from a two-sample problem to a one-sample problem. So I just need to get the confidence interval for these 15 differences, and I can basically neglect where these differences came from in the first place. So let me scroll up so I don't even have to look at those anymore. The average difference works out to be 1.18, while the standard deviation of the differences works out to be 1.1905585097. So that's part of the information that I'll need for the confidence interval. The confidence interval will have the form 1.18 plus or minus a number off the t-distribution, to be found in a second, times the standard deviation, 1.190558, divided by the square root of n, which in this case is 15. So the last piece of information that we need is the area under the t-distribution. This has 14 degrees of freedom. So because it's now basically a one-sample problem, we just do n minus 1 for the number of degrees of freedom for 14. So t-distribution with 14 degrees of freedom. And I need a 90% confidence interval, so I need 90% of the area to lie in the middle. And because there are tails on the side here, that's where I have, because there's tails on the side here, that's why I have a two-sided. Okay, so 0.9, that means that 0.05 lies in either tail. So an aggregate of 0.95 lies to the left of this mark. And so the value of t that I have here will be equal to t dot inv of 0.95 with 14 degrees of freedom. On a calculator, that'd be inv t with the TI-84 and up. This is for 1.7613. And so the margin of error will be equal to, let me write that down on the top first, 1.76131. And so the margin of error will be the product of these things. So that'll be equal to the value of t times standard deviation divided by the square root of 15, which leaves us 0.5414, and cutting it off to two decimal places, 0.54, and the units in this case are hundredths of seconds. So 1.18 plus or minus 0.54 hundredths of a second. That's how to do the problem in Excel. Let me just remind us how to do this on a calculator real quick. So ahead of time, I've already put in the differences, 0.6, 1.7, 1.9, 2.3, and so on. And so if I go to Stat, Calc, 1 var stats, second L1, this will do the same computation that we did earlier in Excel. So the average is 1.18, which matches what we see here, and the sample standard deviation of 1.19055 is what we see here. And then we can proceed with the rest of the calculation as before.